All right, welcome. This is Mrs. Nearing, and I'm going to talk through the problems from this practice quiz on chemical formulas. So we're looking at finding the empirical formula and the molecular formula starting from various methods. And so this first one, we're looking at finding the empirical formula from mass percent data. And so we want to remember our rhyme: percent to mass, mass to mole, divide by small, multiply till whole. So the first step, percent to mass, means we're just going to assume we have a 100-gram sample just to make our life easier. And if we had a 100-gram sample and 53.3% of it was carbon, then we would have 53.3 grams of carbon. And I'm going to do the same thing for all my elements. So I've just taken those percentages and converted them into grams. That is percent to mass. Now I'm going to go mass to mole. So I'm going to convert my masses into moles using the molar masses from the periodic table. All right, 16.0 grams. And when you plug that in your calculator, I end up getting 4.437 moles of carbon, 11.11 moles of hydrogen, and 2.219 moles of oxygen. So you might be wondering why I'm keeping 4 sig figs. Where did she get that from? Well, you just want to wait and round until the end. So I'm just decided to keep 4. If you kept more, that's okay. But what you don't want to do is round early. Okay, so try and wait to round until the very end. Okay, so that's percent to mass, mass to mole. Now I'm going to divide by small. So the smallest number is 2.219. 2.219. I'm going to divide every one by that. And I end up with 1 oxygen for every 5 hydrogens and 2 carbons. My last step is multiply till whole. These are already whole numbers, so I don't have to do that step. So that last step is not always going to be required. So here we go. This is my empirical formula. Empirical formula just tells you the ratio. It tells you there's 5 hydrogens for every 2 carbons for every 1 oxygen. It does not tell you how many atoms are in one particular molecule of this substance. So the molecular formula, like how many things are in a molecule, could be C2H5O. It could be double that. It could be C4H10O2. It could be triple. What would that be? C6H15O3. It could be C20H50O10. It just has to be something that matches this ratio right here. And so we don't really know at this point what the molecular formula is unless we're given some information like this right here. So we're given the molar mass. So the molar mass tells us that the molecule has to have this ratio of 2 carbons for every 5 hydrogens for every 1 oxygen, and the sum of their masses has to add up to somewhere in like the 80 to 90 range. So what you want to do here is first take a look at the sum of the masses in your empirical formula. So if you add all those up, 2 carbons, 5 hydrogens, 1 oxygen, you will get 45 grams per mole. And then you want to compare this to your given molar mass. If they match, then your empirical formula is your molecular formula. But in this case, it looks like it's about double. So if I were to double the empirical formula mass, I would get something right in this range. So that tells me that the molecular formula is double my empirical formula. So if I add up all the masses here, I'm going to get 90 grams per mole, and it matches my empirical ratio I figured out here. Therefore, this must be the molecular formula. If I had added up the masses in this molecule or this molecule, it would be way too high. Okay, it's got to be something right in this 80 to 90 range. So that's how you'd find the molecular formula. Here's an example where we're going to find empirical formula starting from a different kind of data set. This is, instead of being given mass percents of hydrogen and carbon, you combust a sample and you're given mass of water and CO2. So let's write down what we're given. So we know if we combust a sample that is a hydrocarbon, you make 0.102 grams of water and 0.374 grams of CO2. And let's write down what we know. We know we start with a substance that is made of carbon, hydrogen, and oxygen in some ratio, and they are going to react with oxygen in the air and make CO2 and H2O. So this is important because we want to recognize that all of the hydrogens from our sample end up in the water and all of our carbons end up in the carbon dioxide. So if we can figure out how much hydrogen is in my water and how much carbon is in my CO2, it will tell me some information about my fuel that I just burned here. So my first step is, so step 1, I want to convert grams H2O and CO2 to grams H and grams carbon. Okay, there's several different ways of going about this. You could convert grams to moles, and I see a lot of people are doing it this way, so let me write it out this way. So you could convert grams water to moles water. Okay, and then you could say, well, what I really want to know is I want to find grams hydrogen. Okay, so I have to convert moles water to moles hydrogen. And if you look at this 2 right here, that tells me there's 2 hydrogens in every water. And then 1 hydrogen weighs 1.08 grams. So plug that in your calculator, you get 0.0113 grams of hydrogen. Another way of doing this is to find the mass percent of hydrogen in water. And if you do that, I believe if you plug it in your calculator, it ends up being something like 11.1%. So if you take 11% of 0.1, you get 0.01. So you get the same answer. Okay, either method you want to use is good. So do the same thing with your CO2. You can convert grams to moles using the molar mass. If you look at the formula, every 1 CO2 contains 1 mole of carbon. This is a really key step right here, this mole ratio, okay? Knowing that there's 2 hydrogens for every water, but only 1 carbon for every 1 CO2, that's very important. And then 1 mole of carbon weighs 12 grams, so you plug that all in, and you end up with, let me check my math here, 0.102 grams of carbon. And notice how we are told that my original combusted substance also contains oxygen, and the way that we figure out how much oxygen is in it is we look at the total mass of the sample, which was 0.2033 grams. That was the total mass of C, H, and O in your original unknown. Okay. And now I know that 0.0113 grams of that was hydrogen and 0.102 grams of that was carbon. So that means I have 0.09 grams of oxygen in my original sample. Okay, that was a bunch of work just to figure out how much C, H, and O were in your original sample there. And now that I've got grams of everything, now it's just like a regular empirical formula problem where you go percent to mass, mass to mole, divide by small, multiply it till whole. Okay, if we look at that first step, percent to mass. Oh, it looks like they already gave us masses. Okay, so we can skip that step. Now we're just going to go mass to mole. So I'm going to scroll over here to the side. I'm going to convert my grams hydrogen to moles hydrogen. I'm going to convert my grams carbon to moles carbon. And I'm going to convert my grams oxygen to moles oxygen. So I end up with 0.0112 moles of hydrogen. I end up here with 0.00849 moles of carbon, and I end up with 0.00562 moles of oxygen. So I did percent to mass, skip that one, mass to mole, divide by small. So my smallest number is 0.00562. So I'm going to divide everything by that. Boom. And again, I'm waiting to round until the end here. So I end up with 1 oxygen, and this is 1.5 carbons, and this is 2 hydrogens. Okay. So percent to mass, mass to mole, divide by small, and multiply till whole. So in this case, I have a decimal here, and I do need to multiply till whole, so I'm going to double everything. That's going to keep my ratio intact, but it's going to give me a whole number ratio. So instead of 2 to 1.5, it's a 4 to 3 ratio to 2. So this looks like C3H4O2 being my empirical formula. Cool. Okay. Last couple of these should be fast ones. So this one is 2.25. Write down what we know. Okay, we know, the moles of three things. And you're trying to find the chemical formula. Remember, the chemical formula is just a mole ratio. Okay. So the way we find a mole ratio is we do the divide by small step. So you can think of it this way. If we do percent to mass, mass to mole, it's like the first two steps are already done for us. We already have moles. Now we're on to the next step, which is divide by small. So you're going to divide everything by the smallest number of moles. Okay, and that gives you 1 silicon per every 2 potassium, for every 3 oxygen. And then multiply to a whole. Didn't need to do that step. Okay, so that's K2SiO3. That looks like this right here. Problems like this I've seen on the multiple choice section. You want to be able to do them without a calculator. So there you go. Looking down at this one, problem number 4, this is an example of how you might see an application of mass percent. So mass percent on the AP exam, you're not likely to see a problem that just says what's the percent by mass. You're more likely to see it pop up in an application kind of scenario, which is like this one right here. So it's saying a 1 gram sample of which of the following would contain the greatest mass of oxygen. So basically you have the same sample size of all 4 of these substances, and you want to know which one has the most oxygen. So basically you want to know who has the most oxygen per gram. So really what we're looking for is who has the highest percent by mass of oxygen. So the trick to this kind of question is to recognize that, oh, this is really a mass percent. We're thinking about a ratio of oxygen, per gram of this substance. And notice the molar mass is given for you, so nice, you don't have to add those up. So if you think about how you would find the percent oxygen, in your sample, is you take the, mass of oxygen, which would be like 16 in this case, and divide it by the molar mass, which would be 62. If you plug that in your calculator, that ends up being roughly 26%-ish. This one is 16 divided by 40.3. That ends up being 39%-ish. And this one is 16 divided by 94.2. That's roughly 17%. This one is 16 divided by 56.1. That is about 29%. And notice how I said about, like we're not asked for an exact number, so I don't have to worry about sig figs here. You just want to know which of these 4 numbers is the biggest. And this number right here is the biggest. So that means that magnesium oxide has the most oxygen per gram of that substance, okay? So it has the highest mass percent oxygen. So that means 1 gram of it would have the most oxygen in it. And also notice that I didn't even technically have to use my calculator here. I should be able to just glance at these 4 numbers and say they're all 16 divided by something, and this one is divided by the smallest number, so this is going to give me the biggest percent. And this is a question like this has shown up on the AP test before, again on the multiple choice section, so you don't actually have to use your calculator. You just have to kind of have an understanding of ratios and that dividing by a small number would give you a large percentage. So that's another example of how you might see it on the AP exam. Okay, so hope this was helpful. Let me know if you have any more questions.